workshops, and just a little bit before we get started to know what to expect. So these workshops will focus on mostly deep learning and related to AI. So we're going to start off with the basic fundamentals and kind of work our way through until hopefully we're able to learn how large language models work, transformers, CNNs, RNNs, neural networks, all of the architectures that you hear about in research papers and online. We're going to cover all of them. These workshops are tailored towards people who want to know the fundamentals of deep learning. So they're not going to be very beginner friendly, but that's fine. You guys, I think everybody here is going to be able to understand all the topics we will cover. Sometimes they will look daunting, but really once you just focus a little bit, it's very all intuitive and honestly beautiful. Deep learning is an amazing thing. Today we'll be covering neural networks. A lot of you guys have probably heard about them. And they're really the architecture that led to the revolution of deep learning, and you can find them everywhere. So today we will learn just about the base neural networks, how they work, and why do they work. So, a bit of history. Neural networks, and this is very debatable, but some of their roots come from Hebbian learning. They find their way in multiple other places as well. And for a lot of these things listed here, you will also find them being sort of published in different papers by different people at different times, all leading to kind of the same conclusions. In 1958, Frank Rosenblatt, he invented a perceptron, and that is one of the earliest forms of neural networks and very fundamental. 1967, first network was trained using stochastic gradient descent. It's an optimizer for neural networks that we will learn about. In 1969, the same time we landed on Moon, we invented ReLU, which is an activation function. And one of the most important machine learning algorithms to this date, backpropagation, was in the 70s and the 80s. And the reason it's 70s and the 80s is because people would come up with backpropagation, but then there would be another publication with a more efficient implementation, and it would lead eventually to what we have today with backpropagation. And you'll learn what it is, how it's done, and why is it so important. All right, so what are neural networks? You guys probably seen this image about 1,000 times or something similar. So you have some input, and then there's a lot of weights and a lot of neurons, and then you have an output. And so neural networks in general, the easiest way to define them is like a function that takes in an input and then creates an output. And so all you can say is that it takes X and then maps X to Y. And so what are the applications? Well, really everything. And the reason I chose this image is transformers would not exist without neural networks because really they are consistent of them. So that really shows you the power of them. And in general, they're used in machine learning and AI very frequently, oftentimes as a standalone architecture, sometimes as in combinations with others. For example, like here with transformers. And yeah, so really neural networks just map input X to Y. And it's really up to you and your problem what the X and Y are going to be. So it really shows universal application. So you always heard that neural networks learn, right? These models, they are learning, they are starting off from scratch, and they learn something. But how do they learn it? This is like a high-level overview, but we will be covering everything in detail. And it's really simple. So what it does is it computes the output, then compares the output to the ground truth using a loss function. And ground truth is like the actual value. So imagine you are putting in some observation, and you're trying to model some variable. Say, for example, you're trying to predict your GPA based on the amount of hours you studied. So you would put in X, which is the amount of hours studied, and then your model would predict what your GPA is, and then at the end of the semester, you would compare it with the actual GPA you got, and so that's how you would train your model. So after you get the value from the loss function, you would compute all the gradients for all the weights using backpropagation, and then you would just update weights using an optimizer like stochastic gradient descent. We want to put these terms out as soon as possible so you guys get comfortable with them, but you'll get more familiar as we go on. But this is the high-level overview of neural networks and how do they learn. So before we move on, are there any questions? Okay, awesome. All right. So before we move on to the mathematical part, let me give you an example of neural networks in code. Okay. So in these workshops, we're mostly going to be working with pyTorch. pyTorch is a very popular and probably the standard today for deep learning for most applications. So let's start off with a simple example. So here we're going to import all of our necessary libraries. So we're importing Torch, we're importing our function. We'll go over for each of these, so don't worry about that. Then we're going to create a function that we're going to model and our inputs for it. And today we're going to be using a sine function. So using X, we're just going to create a neural network to basically model a sine function. So very simple. And the reason we chose a sine function is because it's very easy to visualize. And so here it is. You guys probably seen this a billion times. All right, so in pyTorch, when you're working with values, you're working with these things called tensors. And tensors are just, think of them as NumPy arrays for deep learning. And you can think of them as matrices, except they're kind of tailored towards parallelization and other aspects. But fundamentally, they are matrices. And so up there, we created two tensors, X and Y. And then here we have this data type, and data type determines what the data type of our tensor is going to be. Very important thing in pyTorch is that when you're declaring types and working with types, they have to be the same. So you cannot multiply a double type tensor with a float 32 type tensor. So they have to be of equivalent d types. So that's why it's always very important to declare d type, so you make sure that they're of the same type, especially because sometimes when converting from NumPy to tensor, the tensor will be of type double, but when you initialize a network, it will be of type float 32. Then we're going to create a tensor data set. You can think of it as like a pyTorch data frame. And then we're going to create a data loader where we put in our data set, and then we do a batch size of 8. So what batch size it means, it's really we're just, on each iteration, we're taking a sample size of 8 from our original data set. And then we just say shuffle to true because it's a good practice to do so. And batch size, we will cover why is it important to always use batch sizes. There is a misconception that it's mostly because of memory constraints, but there are fundamental reasons connected to optimizers on why we do that. But that's not the topic of this workshop. So let's create a simple model. So we'll do class NN, and then we will just make it so it inherits from nn.module. And nn.module is just this container class in pyTorch that gives that class a lot of inherent methods like the forward function and all the other stuff that you'll see. So we will initialize our function, and we're not going to give it any initialization parameters as we're going to do it manually here, which is fine. And then we are going to do, and then just super init because we want to get all of the
methods from our and in the module. So let's start off with creating input layer. So in this case, we have x, and x is just a one-dimensional tensor, and it only has one variable x. So we only have one input feature. So to do that, we need an input layer that accepts a certain amount of input features, then outputs a certain amount of to the hidden size. So we're just gonna do linear 1 equals and then dot here, and we'll do like 100. And I'll explain later why so big of a number for such a simple function. And we're just gonna employ a second linear, and so this is really just a network with input layer, hidden layer with 100 neurons, and output layer that outputs only one variable. And then here we define the forward function, which really just takes is method and takes an x, so x equals dot layer. So first we're gonna take x and we're gonna pass through the first layer, but also we're gonna add this thing ReLU. So I'm not gonna talk much about ReLU right now, but it's very important to use it. It's the activation function that was mentioned, and we'll cover why is it so important. And then we're just going to, again, x equals self dot linear 2, and then x. And so does everybody understand what is going on here? Raise your hand if you're having trouble understanding. It's fine, I'll explain. Okay, so right now we're defining a neural network here, and self.linear1 is the first layer where we have the input size of 1, and then it's outputting 100 size. So that 100 just determines the size of the first hidden layer. Then self.linear2 needs to have its input size matching to the previous layer because of weight matrix multiplications. So we're going to input x into our first linear layer, and then we're going to apply activation function afterwards. Then the output of that is going to be put out to the second linear layer, where it's going to take in 100 variables, latent variables that were created by the first layer, and then they're going to be put through the last layer so that the output is 1. And we'll kind of go over like the dimensions of matrices, and it all makes sense. Yep.
Can you zoom in?
Is it? Oh, can you guys see better now?
Yeah.
Oh, my bad. I thought it was. Yeah, go ahead.
Can you close the...
Yeah. Yeah. It'll be important later because there's a video I want to show. But okay, so we're just gonna define the model, and then we're just going to do that. And simple as that. All right. So now we want to train the network on our data. So what we're gonna do is, let's say, for epoch in range, and let's do 500. Then we will capture losses, and then what we'll do is, so remember we had that loader, right? And that loader is just a data loader. So we put a data set in it, and it creates batch sizes of 8. So on each iteration, we are going to iterate how many times it takes to cover all of the batches in the original data set. So we have to go for loader or for batch loader, and then x and y equal. And so that now we're assigning. So what's going to happen now is that in loader on each iteration, we're getting a tuple of values, and they're going to be x and y. And so here we are just assigning them in this very neat way. But you could do it so that in here we iterate over them. Right? So now what we need to do, before that I forgot, we need to define the optimizer. So don't worry about optimizer too much. Optimizer just Optimizer is just a function that is optimizing the weights of our neural network. So we'll cover it extensively, but for now, just think of it as a function that's making our neural network fit the data. And so we're just going to do torch opt-in, and then we need to pass it the parameters of our model. And then we just need to define the learning rate and cover what learning rate is. Think of it as the how much weights are going to be updated on each iteration, and we'll see how it plays in. And so here we're just going to do or this bit. Right? So then what we need to do is define a loss function, and since this is a regression task, we're just going to do a square function or MSU loss, mean square error, and we'll cover it what it is. But this is just the high-level overview that I want to provide, so that later in the next slides we're gonna build it all up. So we're just gonna do nn.msc loss, and that's perfect. And then we will do output, and then we just put in our x into model, and then we need to compute our loss, and it's very simple to compute the loss. You just put in now, it doesn't matter the order you put it in, because the way mean square error works is that you take the square root of the square of errors, and you'll see in the formula. But pyTorch does suggest using to put in the predicted variables first and then the actual variable second, but it doesn't matter too much. Then we need to do the backward propagation so that we assign gradients to all of our weights. And then we are just going to use our optimizer to use those gradients to optimize our weights. And then, optimizer, it's a misspelling right there. And then we just need to set the gradients back to 0, right? Yeah.
Don't you have to do torch.optim.sgd or something like that?
Oh,
Yep.
yeah, thank you. So we're actually gonna use Atom, since it's faster, but it'll do the same trick. But thank you. And then we just wanna append our losses so that we can later plot them. And this dot item, so what that does is loss is usually going to be a one item. So dot item is very useful because you can extract the scalar value from the tensor. And see, so we're going to train, and then we are going to plot our losses. There we go. All right. So now, since this is a sine function, and you'll see why neural networks have a trouble of modeling something like this. And I have a video of it learning this same function, and it will give you a better idea of how it starts out. So this is the same model, so it's same neural network, and what it's going to do is it's going to start off badly, and then slowly it will go over, and then it will try to fit to the data. And now you would think that this is a very easy function to fit, but we'll go over why neural networks kind of struggle with these smooth functions. All right, and then I'm just going to speed it up, but here we go. Yep, almost there. It might not have enough capacity to do it. I did it in a rush, but we'll see what capacity of a network is and how can you define it so that it can easily model accurately like functions like these. All right, any questions so far? Are we clear on how to train a very simple network? All right, awesome. If you have any questions later, there's going to be a YouTube video, so just make a comment and we'll be sure to reply to it. So make sure to go over it if anything wasn't unclear or anything wasn't clear. But Right? All right, let's get to the fun part, mathematics. So, just gotta grab my mic, second one. All right. So let's start off with output. So what is a neuron? So does anybody have an idea of what a neuron is? Yeah, exactly. And we're inspired by actual biological neurons, where based on the input to the neuron, it will either get activated or it won't get activated. But how does it get activated? Does anybody have an idea how does a neuron get activated?
Because of the bias? It has an activation.
Yep, perfect. Yeah, so here it is. So this is the definition of a neuron. So basically what it is it's a ReLU function, and this could be anything. We just chose ReLU because it's like a standard. There's other ones, but ReLU is very easy to understand. And so it's a weighted sum of inputs and weights plus some bias. And bias, I don't know my opinion about it, but it's more of like an intercept. So don't think too much as a bias, because there's like a lot of biases. There's like bias in errors, there's an inductive bias. So here, let's just call it a bias, but think of it just an intercept. So what you would do is you would take the weighted sum, and then that weighted sum would add a bias to it, and then you would pass it through this activation function called rectified linear unit. And let's start off with the first part, with the weighted sum. So so this is in this form right now. Is there any other form that is worked with, especially in deep learning? Matrices? Yep. Yep. So anybody have an idea what the matrix operation behind this would look like? Say for a 3-feature input. So it has 3 features.
The product?
Close. So it'll just be this, actually. So you would have the first input feature matrix, and then you would transpose the second one. The reason I put the transpose here is because also in pyTorch documentation, they put it like that as well. But it's also nicer to look at the weight matrix like this. But the reason we do that is because we wouldn't be able to multiply these 2 matrices if the second one wasn't applied to transpose. Now, can anybody tell me what a transpose of a matrix is? And why do we need to do it here? Yeah, go ahead.
It's like you're swapping the rows and columns. And
Yep.
It's probably because you make sure multiplication works, so you have the right dimensions to do it.
Yep, exactly. That's correct. So, but can anybody tell me why do we use matrices? Why not just use, say, like a for loop or something like, because summation is really just a for loop. Yep.
Because in GPU, the matrix operations are much more optimized rather than using just the for loop.
Exactly, yeah. You can, pairwise matrices is very easy. Computers love matrices. And that's why GPU computing is so fast for these type of operations. And that's why, in general, GPUs try to make as many CUDA as possible, because then they can do as many floating operations as possible. Now, ReLU, the activation function, is really just you put in a vector or a scalar, and then you just, for each of the inputs in the vector, you decide max of 0 and x. So that means that if it's negative, it's going to get to 0, but if it's positive, it's going to be x. Can anybody tell me why are we doing this? Like, why do we need to make sure that all of our negative inputs are to 0, and then we keep the rest? But don't focus on the negative part. So, given the definition of this, what kind of functions can this describe? Linear, yes. But what about nonlinear functions? Can this describe a nonlinear function? Yes? No? Who votes for yes?
Just because we did it, what, like right now?
No. Actually, no. This, you can stack as many of these as you want. You can have 1 billion layers. They can only describe a linear function, because this is a linear operation. And that is why activation functions are important, because they get these segments that you'll see shortly, so they create nonlinearity within our functions. And so let me show you an example. Okay. So because we had a lot of these. Oh, you're not supposed to see that. That's yet to come, but. All right, so here we go. All right, perfect. So let's create, so here we have a simple model, right? And so what it is, it's a, hello? Did it die? Hello? Okay. All right, so it's a simple linear model. And what we do is we just put a list of hidden sizes, and we just do some Python function to kind of organize it in a way where we can just quickly make our layers. And so we put in our hidden sizes, and we create a bunch of hidden layers. But in the forward function, you'll see that there is not a single activation between them. So we're just stacking and stacking and stacking linear functions, right? And so, and here is just create the output. And then the first one has, so it has, it goes input 1, then it has 3 neurons, and then output dimension is 1. And the second one has 8 neurons, so 2 hidden layers, right? Still linear. So as you can see, we keep adding, but nothing changes, right? The function is perfectly linear. So this is nothing more than just an overly complicated linear regression. So, and you can see that in a nonlinear model. So here we depend on real, right? So we're adding real. So after we input output x out of a layer, we then put it in a activation function. And so we can immediately see here that this function is nonlinear. And I said, whoa. Oh, and then this one as well, right? So this is just a stupid example, but it shows that the activation function is able to add these linear regions. And I'll talk like why they're important. See, now here we have more of them. And so the theory is that the more of these linear regions you have, the more complex functions you can model. So let's go back. All right, so linear region is really just breaking up a function into 2. It's like a piecewise function, right? So you have from x0 to 5, thank you, sorry. From x0 to 5, say it follows one model, and then from 5 it follows a different, right? So it's not linear. That's very important, because when we are working with real-world data, most of it is nonlinear, right? If data was linear, then a lot of the problems would be very obvious. And so for a single hidden layer network, so for a shallow network where we have one hidden layer, for each neuron we add one more linear region. And so that kind of scales up, and you'll see how. So for example, let's look at this function, right? And say we only have 2 regions, right? So we only have 1 neuron, so it can only split the function in 2. Then we add 10 regions, right? So more neurons means more regions. So we're getting closer. Then we add more regions, we're closer again. And yeah, so, and if we keep adding regions, we just get closer and closer to modeling any nonlinear function. Is there any questions about that? Okay. So, yeah, and that
that comes to one very important theorem, and that is that any shallow network with sufficient number of hidden units, and hidden unit is a neuron, can represent any continuous nonlinear function with arbitrary accuracy. So any function that's continuous and nonlinear can be represented with one layer and enough hidden units. So if you have enough linear regions, you can model any function. And this is why we need deep networks, right? You always hear deep networks, right? So it's like here, according to this theorem, why would you need more than one layer, right? You only need one layer, and right, you just keep adding neurons, you'll be able to approximate anything to any accuracy. So I didn't put the assumptions here, but they assume that it doesn't matter just the number of parameters, the way they're organized, but in such way, with one hidden layer, you see the scaling. Number of parameters doesn't scale as much. With 3 hidden layers, we can have a lot more linear regions. And then with 5 hidden layers, it scales so much better. So we're using the same amount of parameters, but we're able to have more number of regions. And why is that important? Number of regions is basically the capacity of the network. So, and this is not always, like your network might not use all of it. So this is the max number of linear regions a network will use given the amount of hidden layers and parameters. So, but still, you want to have as much as capacity for a network as possible. So why would you stick with only one layer? So that's why we use deep networks. Now, I know this could be a hard question, but what happens if we add a lot of layers, like say 50 layers?
I'm assuming the more layers you have, the less optimized it becomes. It takes longer to like train the model.
Yeah, but you know why?
Well, you have more inputs and more like it's more functions it has to go through, so it becomes more complex.
Close. It does. We'll cover it. I just want to see if anybody can get a right answer. But yeah, it does become a little bit more complicated, especially in the backward pass, because you have to store all of the activation functions. But there is another reason that we'll be covering. So let's move on to model learning. Before I do that, any questions about anything here? Yeah. Yeah, so here you can see on the x-axis we have a number of parameters, and that's just the number of neurons. And then here we have number of regions. So the reason that this is the case is because so with hidden layers, the way it scales is that for each hidden layer you add, you get d plus 1 in parentheses to the power of k linear regions. So if you stay with one hidden layer, your how much linear regions you're going to get is going to scale linear, because it's going to scale by d, right? So you would have to have a lot of parameters, and you can see that here that it's pretty much following that distribution. But if you have more layers, then your model is going to have greater capacity. It's going to scale at a much better rate. And a hidden unit is a neuron. And basically the amount of neurons you have is the number of parameters. And so it does make sense to have a deeper network because you're using the same amount of parameters, using the same memory, almost the same memory. There is a little bit of difference, but that's later on. You're not using much in efficiency. You're having a network with bigger capacity compared to just a shallow network. Okay. To move on. All right, so model learning. So we talked about a loss function, right? And so to make the model learn, right, we need to
have it compare its outputs to some function that we're trying to model. So that's how we're tuning our network. And then we use it also to measure model performance. And to give you an example of a loss function, say you have this function, right? You have the predictions in red dots. So what you do is you take the difference between the actual value at some value x, and then what the model predicted, and then you do some calculation, and that is your loss. And in this case, what you see here is a very famous loss function, mean square error, or mean square error, and it's very useful for regression tasks. So usually that's where you would use it. And so how do you calculate MSE loss? And so you just average out the sum of errors squared. So you would take the actual minus the prediction, and then you would square it, and then you would just take the average of that. Also, some of you in your classes might cover RMSE. So RMSE, what it's doing is just adding the root at the beginning, but you can say they're almost the same. Are we good? Yeah.
What's the 1 over n for n?
That is average. So the thing is, your loss always needs to be a scalar. And this averaging is what you'll learn later once you're doing optimization. It's called reduction. So you can't just have a vector of errors, because the way that backpropagation works and how gradients are distributed, you want to have a scalar value, right? So to get a scalar value, you are just going to average this out. And you're not going to lose information, because pyTorch in general stores all of the operations you're doing so that later on it can distribute the gradients properly. So that is why we average it out. And usually that's what you would just average out across all of the data that you measured the errors for. So that is why we use 1 over n, and then this is just summation, and then it goes to n, which is just the number of inputs that we have or number of outputs for our error. And so this is a loss function. So imagine we have a function that has two parameters, w1 and w2, and for y it's the loss. So this is loss for a certain amount of inputs. And why do we need this, right? Why is anybody tell me why is this important, and what do we want to do with this?
It's basically a heat map of how the model will train. For example, we can see some local minimums.
Right.
For example, around 2 minus 2.
Yeah.
But there is a better one at 0 minus at 2, 0.
Yeah. So we want to go there, right?
Yeah.
But do you know this? Like, does your model have information of this when it starts?
No.
No.
Yeah, because computing this would be very hard computation, right? Because usually we're dealing with so many parameters, right? Imagine having to compute this for 1,000 parameters and for 10,000 data points, right? You would have to compute for each of those data points for each of the values of each of the 10,000 parameters, right? It would take forever to compute this. But this is still a good visual example of how a model learns, right? So here we're going to pretend that this, like, we don't know this, but it exists, right? This is factual, right? Given a certain amount of variables, like given a function in a model, this function exists. We just don't know it. So what's going to happen, right? So how do we move down to a minimum, right? So say we start off right here. This is where we start. How do we go down here? Come on, this is calculus, guys.
We
You can multiply the learning rate, like start moving in a direction in terms of changing the weights.
Multiple what?
will take the gradient of the function and we will to point that leads.
But what is a gradient though? Does it go
The
down or
gradient is
up?
the rate of change of the function at any given point.
Right.
So we would want to take that, right, and we would want to move in the direction opposed to the gradient.
Exactly. So we would do it. We would take the gradient, and this is just the gradient of any function. But in our case, this is the gradient. So we have a gradient of a function f, which is a neural network, which takes an x and some parameters theta, and then we're just taking the partial derivatives of loss with respect to each of these weights. So the top, this L is just a loss. All right, so yeah, so let's imagine we start here, right? So we are at the top, our model is doing very poorly, but we want to move towards the minimums. So what do is we take the gradient, and so it's really this partial derivative with respect to our weights, parameters, whatever you want to call them, and yeah, we start moving in the opposite direction, and this is how we would do it. So this is an example of very basic gradient descent. Now, this is not what models use today. There will be a workshop on optimization and more complex techniques, but this is how I started out. So a very simple gradient descent method, assuming a linear function, though, because there are some mathematical assumptions you have to take, you would update the weights by subtracting from the current weights the learning rate multiplied by the partial derivative to that parameter. Yeah?
So for, let's say I am going to the lowest part of the loss on the graph, wouldn't it be, so the time increases as more time spent, isn't the amount of distance that travel get more and more and more?
Yeah, it does. No, that's...
never actually end up at the bottom?
So with this you would not. So regular gradient descent has no considerations of escaping bad local minima. So if you end up in a bad local minima with this algorithm, there's no way of getting out, because when you are down at minimum, all the gradients will be small and you will get pulled in right back in. But there will be another workshop where we will be covering how stochastic gradient descent and Atom and some other optimizers are able to escape these local minima and go towards better minima. But yeah, amazing question. Any other question?
Will we study non-gradient descent based optimizers?
So most of them are gradient descent based.
I was talking something like BFGS, some Haitian.
No. We will really just cover Atom and stochastic gradient descent, since they're like, we don't have enough workshops to cover all of the optimizers, and we do want to go sufficiently at that so that you are able to understand them. Right. And then these gradients get there, right? So there's a lot of operations, especially with a lot of layers. But that's the topic for the next workshop. So this is just a teaser. So this is back propagation. So we will learn how does a gradient go to our parameters. It is straightforward, but also not straightforward, especially for bigger networks. But back propagation has an algorithm that is amazing, and we'll cover it in the next workshop. But so now that we covered this, why don't we create a simple neural network from scratch using pyTorch tensors? Okay, here we go. All right, so we are going to apply a network to the same data set, except now instead of using n and linear, we're just going to be using tensors. So what is a tensor? Like we said, tensor is just a matrix, and let's just see one, for example, torch.rand, and then, right,
So literally like an NumPy array. You can't even spot a difference, right? And so that really makes it easy to work. So let's go back and see what a linear layer is, right? So let's go to here. So we're at pyTorch documentation, and it's very important that you guys get used to using Docu. So documentation is a great resource. It can be a lot faster than using ChatGPT or whatever else you're using. And it also kind of forces you to better learn the library you're using. And pyTorch is amazing. It has amazing documentation. So given all this, can somebody start and tell me like what we would need for a single layer that has 3 inputs and then just outputs one scalar value? So what would we need?
So we would need like a neural network with 3 inputs.
Yep.
1 hidden layer, and then 1 output.
Yep. But let's start off with just making the linear layer. So how do we make a linear layer? So if we go back to our presentation, not here. All right. So how do we make this? Yeah, exactly. We're gonna build a neural network instead of using nn.linear like we did. We're gonna use it. We're gonna do it using tensors.
Generate a random tensor for the weight.
Yeah, exactly. So we are. Where was it? No, not that. We screwed up. There we go. All right. So let's see. Weight1 equals torch.rand. And so given our requirements that it gets in 3 values and outputs 1, what are the dimensions? 1, 3. Yeah, that is correct. But we will be using 3, 1 since it's just a form, but yeah, it is a correct answer. All right, so that's W1. And what is our X? Well, we can just create a torch.tensor of a list, say 1, 2, or actually it's going to be this. So 1, 2, 3. All right. So what about bias? How does bias look here? Yeah, exactly. So bias comes after the matrix multiplications. So what it's really doing is it's getting bias is the size of the output size. So if your layer is outputting 5 features, then the bias is going to be a vector of 5 scalars. But in our case, since it's output 1, it's going to be torch, that tensor, and then 1. All right. So then we will do this. So I don't know if any of you took a linear algebra class or something like that, but usually I want to use add when you're doing this. So you can use the simple multiplication. So then do dot t, that's the transpose, very easy, and then plus b. All right. So that's what I was talking about. When you use lists or NumPy arrays, sometimes it does not convert them all to the same type. So we are just going to implicitly give it all of the types.
Also, the add is matrix multiplication.
Yep. Yep. That's correct. Oh, that is not what we expected. Is it this? No. Oh. No, it was. Right.
There we go. Although that was not what we were looking for. So he has